Dear participants, don't present your screen. We will start the program within few minutes. Our resource person is going to join.
Sir, Manivan sir has arrived, sir.
Yes, sir. Sir, good afternoon, sir. Professor Kaushik, sir.
Good afternoon.
Sir, let me introduce you to participants, sir. Then we will start, sir.
Sure.
Thank you, sir. Thank you, sir. Good afternoon to one and all present here. I welcome all the participants to this Phase 3 6 days short-term training program. Now we are going to start this fourth day and second session. Once again, thank you for joining with us. Now let me introduce our resource person, Dr. Kaushik Paul, Professor, Department of Mechanical Engineering, Indian Institute of Technology, Roorkee, Uttarakhand. Professor Kaushik Paul has completed his doctoral degree in 2009 from IIT Kharagpur. He has started the journey at NIT Agartala as a faculty member and served there during 2011 to 12. His fields of interest are nanomaterials and other high-performance advanced materials. He has published more than 320 research articles in national international journals and conferences. He has citations of more than 1,808 and H-index 24 and I-10 index 51. He is a member of National Academy of Sciences, American Chemical Society, and Royal Society of Chemistry. He has received many honors and awards, and here are the few glimpses. He was honored with IQ BK21 fellowship offered by Korean government for 2 years of research in Republic of Korea. He had DAAD fellowship offered by German Academic Exchange Service for Research in Federal Republic of Germany. He is also a research advisor of Nanyang Academy of Sciences, Singapore. The Institute Research Fellowship offered by Indian Institute of Technology, Roorkee, for 3 years, 2019 to 2021. Welcome you, sir. We are honored with your presence, sir. Now, I request our resource person to continue with the session, sir. Requesting, sir.
Thank you. Thank you very much for the nice introductions. I am sharing my screen. So can you see my presentation?
Yes, sir. Yes, sir. We are seeing, sir. Presentation mode is better, sir. Yes, sir. Yes, sir. Perfect, sir. Perfect, sir.
Okay, good afternoon to all. First of all, it's a great pleasure that I got this opportunity to present my work, or maybe rather I can say that present my lab work in front of you. So basically, my today's lecture has been divided into two parts. So first, briefly, I'll give the outline of the different types of nanomaterials, how we can synthesize those nanomaterials, or how we can characterize those nanomaterials. And then after second part, just I'll give you the brief introductions about that, how we are using those nanomaterials for the various applications. So my outline of the today's talk is that first I'll discuss about the introductions of the low dimensional nanomaterials, and then with carbon and its allotropes, methods for the graphene synthesis, structural characterizations of graphene, multi-dimensional assemblies of graphene, then application of graphene in various fields and futuristic applications, that what we can do in future for the sake of any kind of high-end research in various fields. So first, basically, when I am talking about the nanoscience and nanotechnology, so first one small questions has come to our mind is that what is nanoscience and nanotechnology basically. So whether if we keep any kind of things into the nano side, whether it is known as the nanoscience or maybe the nanotechnology, so it's absolutely not. Basically, the thing is that nowadays nanoscience and nanotechnology is a booming one. So people are using because it is having a very good properties. It is showing very good properties either in terms of the physical properties or maybe the chemical properties or maybe some other means. But the question is that whether all the nanoparticles or maybe the nano fillers or maybe the nanomaterials can show the same properties, or maybe the reason is that why it is showing the good properties too. So I'll briefly discuss about that. So when I am talking about the nanoscience, so basically it is refers to the study. So science means the study, and technology is nothing but the applications. So rather I can say that nanotechnology is the applied of the nanoscience basically. So nanoscience refers to the study, manipulations and engineering of matter, particles and structures on the nanometer scale. So basically 1/1,000,000th of a millimeter, the scale of atoms and molecules. So maybe 1 to 100. So if I am having any things inside it, so basically we are calling it as a nanomaterials or maybe the nano science or maybe the nanotechnology dealing with. So nanotechnology is the applications of nanoscience leading to the use of new nanomaterials. Because new nanomaterials means, why I am talking about the new word is that because every material is having certain pros and cons. So every materials is having some advantages, of course certain disadvantages too. And also from the society point of view or maybe the scientist point of view, our demand is means every time it is increasing. So our demand is every time we want that better properties, we want some better materials, we want certain say suppose lightweight, we want certain kind of properties which suppose the existing material is not giving. So every time for the material scientists, they are trying to prepare or maybe synthesis of different types of nanomaterials and nanosite components in useful products. So if you remember that when earlier days we are having that computers or maybe our storing device that was too heavy, too bulk. So but nowadays it is so small. Even if our mobile is more than sufficient to do all types of works. So which is basically used to talk with somebody else, but nowadays we are doing n number of things through that particular things, and also it is having some storage device, that is we are using certain batteries, so that batteries is consuming the power and slowly it is utilizing. So now you can understand that everywhere we are basically using this kind of materials for this for getting the wonderful properties over there. So basically the nanotechnology provides us the ability to design custom-made materials and products with new enhanced properties, new nanoelectronics components, new types of smart medicines. Yes, of course, all the examples I give you in the subsequent basically. So smart medicines for the basically for the targeted drug delivery, or for the biomedical implant. Basically, we are using these materials. We are using these materials for the sensors like gas sensors, or maybe some toxic gas sensors, or rather humidity sensors, and even interfaces between the electronics and the biological systems. Now, let's start with the talk with low dimensional nanomaterials. So low dimensional nanomaterials, when I am talking about, so when the size of that particular nanomaterials lies between 1 to 100 nanometers. So in one of their axis dimensions. Yes, why one of its or their axis dimensions I am talking about? Because you probably heard about the 0D, 1D, 2D, 3D. So these kind of materials. So it totally depends upon that how many X, if I take the X, Y, and Z, so whether X is into the nanometer and Y and Z is into the micrometer range, or maybe both are into the nanometers, one is into the micrometer, depending upon that, basically we are classifying it as 0D, 1D, 2D, something like that. This nanoscale size affects the material's ability to acquire the electronic quantum confinement. Yes, of course, because its electronic structures, its total band gap, bandwidth, everything is totally different. So of course they are giving certain kind of, some materials are behaving like a conducting material, some are semiconducting materials, some are insulator materials, and of course when I am making the small size, automatically its surface to volume ratio is increasing tremendously. So when I am having the surface to volume ratio less, so automatically it is exposing a higher surface area, so due to which it can interact with the other things, it can show the better properties. So these are represented by nanoparticles, either or maybe the nanorods, or maybe the nanofilms, and maybe the nanocrystals. Now come to the types of the low dimensional nanomaterials. So probably you have heard that there are n number of different types of nanomaterials, but if we do proper classifications, maybe some nanomaterials will come or will form a particular group. So first, basically, we are talking with the graphene. So this is a very excellent example of the nanomaterials. So basically, the graphene and allotrope of the carbon is the form of a single layer of atom in a 2D or maybe the two-dimensional hexagonal lattice, in which one atom forms each vertex. So right-hand side corner, you can see that that is the very good examples of the graphene itself. Or rather, I can say the graphene sheet. Basically, it is an example of the single layer graphene sheets. So basic structural element of other allotropes like graphite, charcoal, carbon nanotubes, and the fluorine. So basically, the graphenes are formed from the graphites. So from the graphite, we can pursue, or maybe we can get different types of nanomaterials basically. Then we are having that covalent organic frameworks. In short form, probably you have heard about the COPs. So 2D and 3D organic solids with extended structures in which building blocks are linked by strong covalent bonds. So you can see that in between that it is forming some strong covalent bonds. So it is very, very hard and it is very difficult to segregate. So they are porous and crystalline and are made entirely from the light elements like hydrogen, boron, carbon, nitrogen, and oxygen. So these all are the things. Then we are having that metal organic frameworks, that is the MOX. So crystalline porous solids composed of 3D network of metal ions. So you can see it's a kind of cage-like structure basically. So metal ions held in plates by multi-denate organic molecules. So organic ligand are there, so some metal nodes are there. So basically the structure is like a metallic structure kind of thing. So MOX have a high microspore volume crystallinity and high metal content, offering potentially valuable active sites. They can be used for gas storage. Yes, nowadays people are talking about the hydrogen storage basically. So hydrogen storage, or maybe any type of volatile gas storage people are using. People are using it for the purifications and separations, basically for the water purifications or something kind like, because it is having the porous in structure. So it is very good for preparing any kind of membranes and bulk catalysis and sensing applications too. Then we are having that black phosphorus. So that is, in short, it is known as the BP. So it is natural p-type semiconducting materials in which each layer is vertically stacked by the van der Waals force. So basically in between the force, van der Waals bond are acting, and basically from the black phosphorus people are using the phosphorine, which is having a very good examples, and we have already used this particular phosphorines in our lab for the sensing applications. In a two-dimensional form, it is known as phosphorine, has similar properties like graphene. So it is almost same like graphene, other to be semiconductors such as graphene. Then it is a very good examples of the transition metal dichalcogenides, so TMDs. So this is also the new family to be nano in the form of MX2. So M stands for transition metal and X is the chalcogens basically. So basically the molybdenum sulfide, if I talk about MOS2, so that is the another examples of the transition metal dichalcogenides. WS2, tungsten disulfide, then molybdenum disulfide MOS2. So these all are the different tellurium sulfide TES2. So these all are the different examples of the TMDs. Now come to the HBN or maybe the hexagonal boron nitride. So two-dimensional hexagonal boron nitride is an isomorph of graphene with a very similar layer structure. It consists of alternating boron and nitrogen atoms. So basically you can see over here that we are having that boron and one nitrogens. So subsequently, so basically what is happening, so it is having the sp2 bonded network with each layer, and the bond length of B and N is basically 1.44 angstrom, while that Cc in graphene is 1.42 angstrom. It is an insulator with excellent thermal stability, chemical inertness, and unique electronic and optical properties. So basically, when I am giving the examples of different types of nanofillers, let me clear another one very beautiful questions that all the nanofillers is giving very good properties, but the thing is that why we are not using all the properties or maybe all the nanofillers. Electrons available to form covalent chemical bonds at the outer shells, It belongs to group 14 of the periodic table. So you can see that is standing at the 14 number in the periodic table over there. So basically, in the carbon, if you see that it's basically known as 12C, I am talking about. So it is having the 6 protons, 6 electrons, and of course 6 neutrons to neutralize. And electron configurations is 2 and 4. So 2 is the inner cell or maybe the first cell, and 4 is the outer cell or maybe the second cell. Next, what are the allotropes of the carbon? So there are n number of of course there are so many types of carbon allotropes are available right now, but I can explain you very precisely so that you people can easily understand that what are the different types. So first one is known as the Fullerene. So Fullerene, it's nothing but looks like a soccer ball basically. So a form of carbon having a large spheroidal molecule consisting of a hollow cage of 60 or maybe the more atoms. So basically it's known as the zero dimensional or maybe the 0D. Then examples, Buckminster Fullerene has a molecule with 60 carbon atoms that are arranged regular pentagons 12 and the hexagons 20 to form a hollow cage-like structure. So this is the example of Fullerene. If I talk about the nanotubes, so nanotubes is nothing but if I cut this particular football, I can get a sheet. And then if I wrap or maybe the roll that particular sheet, it will form the nanotube. Nanotubes also are different types. Sometimes we are calling it as a single wall nanotube. Sometimes we are calling it as a multi-wall carbon nanotubes, MWCNT, or maybe MWNT, SWCNT, or maybe the SWNT. Sometimes we are calling it as a double layer nanotubes also. So it depends. If you are having, suppose if you are having a 4 number of pages together and you are rolling up, so that means inside you can see there are 6 pores or maybe 4 pores has been formed. So that is the best example of the multi-layer or maybe the multi-wall carbon nanotubes. Now, if you are having a single page and if you wrap it, so automatically you can get it a single one. So that is nothing but the single wall nanotubes or maybe the single wall carbon nanotubes. Then come to the graphene. So graphene is an allotrope of carbon consisting of a single layer of carbon atoms arranged in an hexagonal. And of course, the last one is the graphite, which is the best things. So graphite is a crystalline form to element carbon with its atoms arranged in a hexagonal structure. It is soft, black, lustrous form of the carbon. Basically, the pencil lead is the good examples of the graphite. Now, generally people are telling that graphite is the main thing by which or maybe from which we are getting all the things. But actually, that Professor Gim and Professor Novosela, who is the inventor of this particular graphene. So basically, they are telling that graphene is as the mother of all graphite form. So if you are having a single sheet, if you can make it a ball, so it will form the C60 or maybe the Fullerene. If you wrap it, so automatically it will form the carbon nanotubes. If you take so many pages and stack together, so it will form the graphite. So graphene, a single layer, is basically the mother of all the graphite form. Next, what is the graphene discovery? So in 2004, graphene was first isolated by Professor Andre Gim and with former student that Konstantin Novoselov at the University of Manchester, England, by which they got the Nobel Prize in the year of 2010. So basically, you can see that I have given one examples of the Scotch tape methods over there, which I'll come into the later in details. So basically, you are having that graphite, which is nothing but the stacking of the graphene sheets together. So if you are able to take out only a particular sheets from there, so automatically you can get the graphene over there. So it is the one sheets over there. So it is a stacking, which is nothing but forming the graphite. So graphene is an atomically thin and two-dimensional sp2 hybridized form of the carbon. So now graphene properties. Basically, why we are using the graphene? Because it is having or maybe it is showing very, very good properties over there. So first is that if I talk about the mechanical properties, yes, was thinnest material, only one carbon atom thick, around 0.34 nanometer. structures, one sheet thickness, several times stronger than the steel at that particular thickness, stiffer than the diamond, flexible and stretchable, lightweight. So that's why people are using graphene for their mechanical purposes. If I talk about the chemical properties, so chemically most reactive form of carbon, only form of carbon in which each single atom is an exposure for chemical reactions from two sides due to the 2D structure. So C and C, top and bottom C, are totally vacant. So basically, if you use it, so any kind of reactions can be possible with that particular free carbon over there. So carbon atoms at the edge of the graphene sheets have special chemical reactivity, chemically modified with oxygen and nitrogen containing functional groups. So we are that's why we are able to do some types of putting, or maybe some types of doping, or maybe some types of interactions, and we can use the graphene for the chemical purposes. If I talk about the thermal properties of that particular graphene, so thermal conductivity of the material relates the heat flux per unit area. So thermal conductivity of graphene is much higher than all other carbon structures as carbon nanotubes, graphite, and diamond, basically at the room temperature. If I talk about the optical properties, it is transparent. One atomic thick layer sheet absorbs almost 2.3% of the visible light. So that is also a very important parameters. If I talk about the electronics, most probably everybody knows it. So basically it is having a very high electrical conductivity. Electrons are able to flow through graphene more easily than through copper. So that's why it is having a widely used for the electronic or maybe the electrical purposes. Now, if I talk about the electronic properties, so basically, because other properties are already there, so I am basically giving the emphasis on the electronic properties, that why it is showing its. So graphene is a planar sheet of carbon atoms arranged in hexagonal rings, which forms the honeycomb lattice. So basically, we are calling it as a honeycomb structure, basically. So in the term of molecular orbital theory, its atomic structure is characterized by two types of CC bonds. That one is the sigma bond, another one is the pi bond, basically. So basically what is happening, sigma and pi constructed four valence orbitals of carbon atoms, that is the 2s, 2px, 2py, and 2pz. So basically that is the formations over there, where a z directions is perpendicular to the sheet of graphene. So from this image you can better understand that how it looks like. Basically each carbon atoms bonded to three carbon neighbors via in plane sigma bonds form the sp2 hybridized orbitals. So orbitals formed from one s orbital and two p orbitals, basically, while the fourth remaining pz orbitals give rise to a highly delocalized pi orbital, and its electron is free to move. So that's why we are getting a very good electronic properties over there. So the bonding pi and the anti-bonding pi prime, so top and bottom basically orbitals, so pi and pi prime, basically the wide electronic valence and the conduction bands, it looks like this. So basically this is the sigma bond, so basically in between it and the pi bond is creating in between these two. Next, in graphene, conduction and valence band touch each other in one point at 6 corners, so two-dimensional hexagonal brilliant zone, and create the zero band gap. So that's why we are getting a very good electronic properties over there. So they touched each other. So if the conduction band and valence band gap will be more, so automatically it will act as a insulator, and if it is closure, then it will act as a semiconductor, and when it is touched, so basically it will act as a metal kind of things. So it is a zero overlap semi-metal with very high electrical conductivity. Electrons are able to flow through graphene more easily than copper. The electron travel through the graphene sheet as if they carry no mass, as fast as just 100 that of the speed of the light. So now you can understand that why it is giving a very good So people are using N2H2, some people are using NaBH4, some people are using only the temperature or maybe the heat. But everything is having certain drawbacks. So basically we have used the NaBH4 in our case because we have seen that yield value of the graphene, reduced graphene oxide has been increased, and the maximum functional groups has been removed from that particular system, so that it is having very good active sites which can be used for the future applications. Of course, there are certain drawbacks for the thermal one also, because thermal one you are heating it around certain temperature, say suppose 1000 degrees centigrade. So what is happening? The material is basically the decomposing. So that is also the another drawback for using the thermal one. So there are different methods. So basically we are using with the NaBH4. Now come to the graphene quantum dots. So GQDs are 0D materials derived from both graphene and QDs called as small piece of graphene. GQDs stand out as unique quantum size graphene crystal structure. High specific surface area because size is too small, with appropriate surface modifications enables them to be ideal nanocarriers for the drug delivery. Yes, we have used these graphene quantum dots for the targeted drug delivery applications for the cancer therapy. Basically, we are working on the breast cancer and as well as the lung cancer of the system. Recently, we have started the working with for the bone cancer system. So basically, we are using the graphene quantum dots. Of course, it is having very certain good advantages also due to their low cost, abundant sources, excellent photo and chemical stability, and super biocompatibility, because you are injecting these materials inside the human body. So this material should have very less toxicity. It should very, very good compatible with your organs or maybe with your bloods or maybe the proteins, so that there should not be any side effects inside your body. And not only that, after completing its particular job inside the body, it should come out from your body, so that in future there should not be any kind of side effects or maybe any kind of disturbance. Now, how people are doing the graphene quantum dot synthesis? So basically, there are so many methods also there. So they are having the graphene sheets, they are grinding, vigorous stirring and shaking, followed by the sonication methods. So simple, the small portions they are tearing up from the graphene sheets itself. So it is the before configuration centrifugations, and after 10,000 RPM centrifugations, they are getting GQDs of the centrifugations, and you can see the liquid color. So it is almost like transparent, but still the quantum dots are present over there. And in this particular case, they are doing the microwave irradiations over there. So they are cutting it into the different small pieces, and then they are using the NaBH4 for 2 hours at room temperature, and they are forming the synthesis of the graphene quantum dots with the microwave approach. Now come to the structural characterizations of the graphene. Yes, this is also another thing, because every time we are talking about the nanomaterials, nanocomposites, so when we are working with the nanomaterials or nanocomposites, so we should have some clear knowledge, because I can tell you one story is that for the nanotubes, the Professor Ijima, when he has developed this carbon nanotubes, or maybe rather I can say discovered this carbon nanotubes in the year of 1991, so he didn't get the Nobel Prize. But who has discovered the graphene? So in 2010, so Professor Game and Professor Novoselav, they got the Nobel Prize. Now the question is that why Professor Ijima, who has developed or maybe who has invented the carbon nanotubes, has not got the Nobel Prize? The question is that the general myth is there that it is already present in the nature, but till now nobody has shown it to the systems, so it is not that new up to that much level. So now the question is that when we are also working in the lab, we are doing so many chemical reactions, we are using so many things, and now the question is that sometimes it may happen that by unknowingly we are throwing something, or maybe we are not using certain things, but it is having a very good properties, or maybe some new materials has formed, but due to the lack of the knowledge, we are thinking that is the wastage of the material, simply we are throwing. So that's why the main role of the characterizations, because if we do the characterizations and if we know the characterizations of materials, or maybe sometimes it may possible that we can get certain kind of by using the proper characterization techniques for that particular materials. So basically, when I am talking about the different types of structural characterizations, so basically we are using the transmission electron microscopy, that is short form is known as the TEM, but nowadays people are using the HRTEM. So it is going around 1 nanometers, 2 nanometers range. So high resolution transmission electron microscopy, we are using the scanning probe microscopy, we are using the Raman spectroscopy, we are using the optical microscope also. So basically the transmission electron microscope, as I told already, so it is having a very good electron microscope. Basically the electron in a high rate, it is passing through that particular materials, and it is giving the structure, or rather I can say the morphological structure of that particular materials. I am not going into the details that how basically the transmission electron microscope works. So basically by this you can easily go up to the 2 nanometers or maybe the 1 nanometer range, and you can easily identify the nanoparticles or maybe the nanomaterials. Not only that, you can do the index studies with this one also, or maybe some kind of chemical composition studies by which you can see that what type of materials are present over there, what is the percentage of materials present over there, so that you can get a rough idea that what type of materials has been formed from there. Also, you can go for atomic force microscopy. So this is also will give you the surface properties, or maybe the surface roughness, or maybe the some profile of that your particular materials, or maybe the thin films. So basically you can get certain informations. So here is the image of the transmission electron microscopy. So the picture shows a graphite sample that was imaged by scanning tunneling microscopy STM. The scan rate of entire image is less than 7 nanometer. Excellent atomic resolution has been achieved. So this is the TEM image, and this is the image of the scanning tunneling microscopy. So this is the Raman analysis of the graphene. So it can, from the Raman, you can get some D band, G band, some 2D band over there, and easily you can calculate that ID by IG or maybe I to D by IG ratio, so that you can easily find out that what type of materials, or maybe exactly you got the graphene or not, or maybe some impurities are present or not. Also from the Raman, you can get whether 1 layer, 2 layers, 3 layers, or maybe 4 layers has been formed or not, because you know in between the layers that how much distance are there, so easily you can calculate that how many layers has been formed by the Raman analysis. Then you are having that optical microscope analysis, but the optical microscope analysis is not about the nanometer levels. Yes, true. So it will give you the image of the micrometer scale. So basically for the metals or maybe some other things, we can do the optical micro image. Or maybe if you are having very high resolution optical microscope, maybe you can get the, or maybe you can see the graphene layer. So here by coloring, you can see that it is very light in color. So it is having a 1 layer, it is 2 layers, it is 3 layers, 4 layers, but it is not, or maybe rather I can say it will not give you that 100% layers result like TEM or maybe the FACM or maybe the Raman scoping. Now, I am going to talk about the multidimensional assemblies of the graphene. So graphene-based 1D macroscopic structures, graphene-based 1D macroscopic structures, and the 1D, 2D, and the 3D macroscopic structures. Basically, I am going to tell you. So when I'm talking about the 1D macroscopic structures, so graphene fibers and the ribbons is the best example of the one-dimensional. So it includes the rational design and construction of the graphene-based macroscopic assemblies with 1D. So here you can see that you are having that graphite oxidized to graphene oxides, geo nanoplatelets, and sonicate to disperse in water as a liquid crystal, which is known as GOLC. So basically then GOLC through syringe you are injecting into some coagulant bath to make the fiber. So continuously you are maintaining that particular pressure, so that liquid is directly coming into that particular bath and the wash bottle of the methanol. After that you are cleaning it, and then you are taking the graphene fiber over there. So graphene oxide fiber wound on reel, then reduced with sodium borohydride to form the graphene fiber basically. So this is the very nice examples that how we are preparing the graphene fibers. Then graphene ribbons. So basically structure, one can employ the organic chemistry principles for attaching a range of biomolecules onto the graphene itself. The unique optical and electrical properties of graphene can be exploited for the bioimaging purpose. This is the foremost main applications of this one, because I can see it from the outside, so I can see that how my medicine is traveling, how I can see that how my medicine is killing the affected sites, or maybe how it is reaching to the systems. So that is having a very good unique optical and electrical properties of the graphene itself. Then I am having the graphene is a mechanically robust material, so its unique structural and mechanical properties together with its compatibility with biological molecules in general allow its use for tissue and the genetic engineering. Yes, nowadays people are working for the tissue engineering, or maybe the packaging applications, or maybe some kind of biomedical applications. People are working on the bio implants. People are making certain kind of stents for the heart disease problems. People are using certain kind of artificial bones, or maybe the artificial nerves, where people are widely using the graphene. Then graphene serves as a platform for preparations of composites. The platform combined with other nanoscale materials can be special agents with biological activity and the applications. So thus the graphene basically it's widely used for the biomedical applications nowadays. Now I can give you the examples that different combinational attributes of graphene for application opportunities. So graphene, it is having a very less cytotoxicity, it is having a very good biofunctionalizations, it is having a very good biocompatibility and biorecognition. Thus, it is the combinatorial attributes of the basically of the graphene. So that's why we are using it for the antibacterial applications. We are using for the cancer phototherapy. We are using it for the bioimaging. We are using it for the drug delivery systems. We are using it for the genetic engineering. We are using it for the immunosensor, and we are using it for the tissue engineering. Also, there are n number of applications basically where you are using the graphene. So probably you have gone through some literatures, and that nowadays in these pandemic situations, people are using the N95 masks. And if you see clearly that in some companies or maybe some masks manufactured, basically they are using the graphene layer over there. So it is very good cage-like structure, so it can stop the virus or to go inside. So that is also the another example. Sometimes you can see that some news that some people are using it for the water purification purpose. So graphene is having enormous applications for the biomedical point of view, where people are using the graphenes into their various forms. So basically, people are working on the gene therapy, people are working on the tissue engineering, bioimaging, biosensors, antibacterial agents, 3D bioprinting, photothermal therapy, and the drug delivery. So there are enormous applications of the graphene. Now, graphene in the targeted drug delivery. So basically, what is happening? So basically, the graphene we are using either maybe the GO, RGO, but maximum cases we are using the RGO. Basically, we are having the targeted molecules over there, and we are having the drugs. Now you can see that you are having the sheets of there in which you are putting the drugs over there. So you are having some targeted molecules. So this is the stimulated release. Basically, this is the tumor sites over there. So now what is happening? The tumor sites is having certain kind of targeting molecules. So when these targeted molecules will match with the targeted molecules of your particular drugs, then only it will reach at that particular point over there. It will stay over there. Slowly it will release the medicines over there, and then after that it will come out from the system. So like this way, basically we are targeting the actual cases, and it can cure. Now the question is that you may ask the question that why I am calling it as a targeted drug delivery. Yes, of course. So suppose I can give you an example. Suppose if somebody is having some headache, or maybe some pains, joint pains over there, maybe hand or maybe the leg. So what basically we are doing? We are taking the paracetamols, right? So when we are taking the paracetamols, of course, it will reduce your headache, it will reduce your joint pain, and it will reduce any kind of pains if it is present inside your body at that particular time. But that you have taken that particular medicines for a particular purpose, either for the headaches or maybe that particular pain. So now you can understand that when I am taking any kind of medicines over there, the medicine is working from my head or maybe from my hair to from my foot. So the whole area the medicine is covering. So now it is paracetamol, it is less dangerous to the body, but when I am injecting certain kind of high dosage of medicines, like any kind of cancer medicines or maybe any kind of high antidotes or maybe the anti kind of things, antiviral medicines over there. So what is happening? It is going to the good cells also, it is going to the bad cells also. So what will happen? It will kill certain kind of bad cells, simultaneously it will kill some good cells also. And that basically is known as the side effects of any kind of medicines. But for the cancer medicines, I cannot take that particular risk because it should not kill the good cells, because I need the good cells, because my good cells numbers are decreasing very rapidly. So I have to save the good cells, but simultaneously I have to kill the bad cells too. So thus we are taking this kind of technology by which the medicines will directly go to the bad cells, it will kill the bad cells, and it will not harm with the other things. And also the thing is that when there are certain kind of things basically which should not directly come into the contact with the body as early as possible. So what will happen that I'll come when we are doing some work, we have done already some work. So when I'll explain that particular thing, so I'll tell you that why basically we are doing this kind of technology. So now if I talk about the graphene based biosensors, so there are so many things. So analytes, so small molecules, proteins, cells, nucleic acids. If I talk about the receptor kind of things like enzymes, antibodies, nucleic acids. If I talk about the graphene transducer, that is the G electrode, GFET, transparent G substrates. So these all are the examples of the different types of biosensors. Now, graphene based nanocomposites prepared in our group. The polymers nanocomposites, some metal matrix nanocomposites, some formations of the graphene oxides, reduced graphene oxides, and the metal oxides. And the applications are batteries, supercapacitors, fuel cells, solar cells, and the biomedical applications too. So first, we are going to start with the graphene for the energy harvesting systems. So I told you that what is the use of the graphene for the energy harvesting. So basically, we are talking about the triboelectric nano generator. So when I am calling it as a triboelectric nano generator, the tribo is nothing but the Greek word whose means is that to rub, means rubbing. So if we rub two surfaces, so another examples I can give you that in winter. So when we are feeling certain cold or certain things, or maybe we are getting up in the early morning. So basically, if we feel cold, what we are doing? So simply we are taking two palms of our two hands and then we are rubbing. So when we are rubbing, so we are getting certain kind of heats over there. So that means that particular tribo or maybe the friction has converted into the heat. In this particular case also the same thing, we are rubbing it and by that we are generating certain kind of electricity. So basically it is an energy harvesting device. It converts the external mechanical energy into electricity by a conjunction of triboelectric effect and one electrostatic inductions. Principle: triboelectric effect is a contact induced electrification in which a material becomes electrically charged after it is contacted with a different material through friction. So one is become positive and one is become the negative. Electrostatic induction is a method to generate static electricity in a material by bringing an electrically charged object near it. Yes. Now we can see that there are four types of. Now this is the short form, basically triboelectric nano generator. That is in short is known as the TENG basically. So TENG is nothing but the triboelectric nano generator. And there is four types basically. One is the vertical contact separation mode. One is contact sliding mode. One is the single electron mode. Another one is free basically RGONR, that is reduced graphene oxide nano ribbons. We have prepared, so its structure is something like that, and then we have used the Captain film with RGONR film and AI film, the aluminum film, and PMMA sheet as a segregate and the ground. So basically, we able to prepare the voltage at that first instance. We have done it maybe 4 years back, 2016. We have published our first papers. So at that time we are able to make around 0.4 volt. Now after that we have reached around 2.5 volt till now. So applications basically, so for touch sensing, you are using the continuously keyboard over there. You are using some self-powered pressure sensor. So you are using the door knob or maybe the door handle. You are using the calculators. You are using the powering wearable devices, self-powered wearable, flexible patch for robotic manipulator, charging electronic gadgets. So in number of places you can use this kind of energy generation systems. Now come to the battery, basically, not battery, basically supercapacitor. So I'll give you an easy examples that what is the meaning of the supercapacitor and what is the meaning of the battery itself. So basically, if you see that we are working on the supercapacitor side basically. So what is the basic difference? So both are storing the energy, both are releasing the energy. But now what is the difference? The difference is here, one is the short distance runner and another one is the long distance runner. So when I am talking about the short distance runner, say for 100 meter for the Usain Bolt, so what he needs, 100 meter or maybe the 200 meter, very short durations, he needs all his energy. So within 200 meter or maybe the 100 meter means within 9 seconds, 9 point something seconds, he is utilizing his whole energy over there. So that is the example of the supercapacitor. So higher power handling capability, long cycle life, basically 50,000 rechargeable cycles, fast charging and high temperature stability. But when I am talking about the battery, that is the long range runner. So basically for the marathon runner, he is going to kill his whole energy for 5 kilometers. So his energy release rate is very, very slow. But for supercapacitor, the energy release rate is very fast. So basically low power handling capability, smaller cycle life, few hundred to 1,000, slow charging, smaller temperature stability. So that is for the basically battery. Now if I go through the Raman plot between energy and power density, so you can see if I talk about the power density, so it is the ultra capacitors or maybe the conventional capacitors. So ultra capacitors stand over here, which is having a high energy density and the power density is also high. But when I am talking about the conventional batteries, the energy density is high, but power density is low. If I talk about the fuel cells, it is having the very high energy density, but very low power density. So now we can easily understand that what is the difference between the supercapacitor and the battery. So now electron materials and related storage mechanisms used for supercapacitor, basically the carbon-based materials people are using. So like carbon nanotubes, graphene, graphene oxides, graphene nanoribbons, activated carbon. So you are activating the carbon to energize it, carbon aerogel. So basically the storage mechanism is known as the electrolytic double layer capacitance, EDLC. If we go for some metal oxides, so basically the storage mechanism will be different. That is the redox type pseudocapacitive storage. So manganese dioxide, iron oxides, cobalt oxides, nickel hydroxides, these all are the examples. Now if I talk about the conducting polymers, so basically the polyaniline, in short basically known as PANI, polypyrrole, that is PPY, polythiophene, that is PTH, etc. all are the examples. The storage mechanism is either redox type pseudocapacitive storage. Now in our lab also we have done certain work with the carbon nanotubes and polyaniline with the graphene oxides on nickel foam basically. So we have introduced the nickel foam. So it's a case-like structure. So basically we have used it for the supercapacitor application. So first we have multi-phase structured Pani anchored CVD grown MWCNT on RGO coated nickel foam for binder free supercapacitor electrode. Basically we have used. So we have published this one in the Electrochemical AICTE already. It's a long back, 3 years back. So now what is that? Basically this is the solid state supercapacitor. But nowadays we have moved to the liquid based or maybe the flowable supercapacitor. Then we have done certain work on the fabrication process of the polyaniline and polypyrrole with the graphene oxides composites basically. So this one, it has been observed that the specific capacitance improved by 95.45% with the additions of the polyaniline. However, polypyrrole coating over geo increases its specific capacitance by 22.73. So when we have used the polypyrrole, the capacitance, specific capacitance has increased. The kinetic difficulties for both charge transfer and ion transport were reduced effectively throughout the electrode due to addition of geo, allow in case of PP, why the storage capacity is enhanced due to the synergistic effect between the geo and the polypyrrole. So this is the cyclic voltammetry of the geo, PEG means polyaniline graphene, and the polypyrrole graphene. Now, what are the advanced applications of the supercapacitor that people can think of? That it can be used nowadays. People are using for the Apple iWatch, transparent mobile phones, the electronic vehicles, the Google Glass, the artificial electronic skins. So basically, the people are using, or maybe it can be worked out. Now come to the graphene for the hydrogen storage. So one of my students, she is working on this particular topic. So hydrogen is the most common element in the universe and has the potential to become an inexpensive source of energy for vehicles and industry. It is a green energy carrier that is 142 megajoule per kg, and in order to efficiently use hydrogen and storage of hydrogen is very important. Yes, because maybe after 20 years or 30 years, this coal or maybe the petroleum products is going to be finished. So but we cannot close all the lights or maybe the fans or maybe all the equipment. So we have to generate the electricity in some other means, or maybe we have to generate the power sources by some other means. So now people are tending to move towards a renewable energy and hydrogen storing and utilizing the hydrogen, because hydrogen is never-ending process, getting the hydrogen, and always will get it from the water itself. So it is maybe if we use or maybe able to use the hydrogen as a gas for the energy generation, so maybe the problem will be solved and it can sustain for a quite long time. Porous materials with large surface area are quite suitable to store the hydrogen. I have already explained to you. Carbon-based materials like graphene can efficiently store hydrogen as compared to other materials, as graphene-based materials are relatively light, having good mechanical properties and flexibility. Graphene favors good dispersions of catalyst nanoparticles, which further improves the hydrogen storage capacity. We attempt to incorporate graphene with metal and metal oxide nanoparticles. Yes, we have used already with the graphitic carbon nanotubes, GCN. We have used certain kind of graphenes, nanoparticles as the hydrogen spillover phenomenon helps for hydrogen storage in these particular materials. So we are using the hydrogen tank over there. We are using the fuel cells. So from fuel cells, directly the energy is going to the electric motors by which you are running it. So from this particular, the fuel cell concept has come, which I'll briefly explain in my subsequent slides. So it will generate the water and heat. It will absorb the oxygens with the hydrogen, and of course, hydrogen and oxygen reactions. It will generate the water and the heat. So that heat, it will rotate the turbine kind of things and the propeller of that particular electric motor, and it can generate the electricity. So now, if I talk about the electrochemical hydrogen storage capability or the zirconia-coated reduced graphene nanocomposites. So high surface area, that is 394 meters square per gram, and good porosity, that is 20.56 nanometer, zirconia oxide coated RGO nanocomposites was synthesized. Strong hydrogen desorption peak was obtained at minus 0.6 volt for zirconia oxide RGO in an anodic region, shows good hydrogen storage as integrated hydrogen oxidation charge was calculated to be 502 MC. So this is the pores of the graphene sheets over there. So highly porous nanocomposites, this one, zirconia incorporated on graphene oxides. So where we can store the hydrogen over there. So nitrogen absorption, desorption, pore with distribution analysis, we have already done. We have done the CV analysis also there. Now applications. So a lot of work is being done in the field of hydrogen by the government of India. Though much work is in the research and development phase, few of the projects undertaken by the research institutes and industries in India are as follows. Say, with a view of capacity building in hydrogen energy sector, a national center of excellence for hydrogen energy and fuel cells may be set up in the country in Walpahari in Gurugram. So these all are the examples. Indian Oil Corporations, the country's largest fuel retailer, successfully demonstrated the trial run of India's first hydrogen fuel self-powered bus in collaborations with the Tata Motors. IIT Delhi developed a hydrogen fueled engine for a three-wheeler in association with Mahindra and Mahindra. Hydrogen fueled internal combustion engine for stationary power generations. Idea Cellular, a telecom power tower operator, has installed a polymer electrolyte membrane fuel cell systems to provide backup power to a telecom tower in Madhya Pradesh using the hydrogen supplied from the nearby chloroalkali unit. So these all are the examples. People have already started, but they are a long way to go. Now, this is the examples. So what is the polymer electrolyte membrane fuel cells? So how the PEMC works, basically, right hand side image. So before going to see that particular image, let us start with this one, that what is the PEMC basically. So it consists of an electrolyte membrane sandwiched between an anode, negative electrode, this is the anode, here platinum catalyst, and here also the cathode is also the platinum catalyst. So positively electrode. Description: a thin solid organic compound, typically the consistency of plastic wrap and about as thick as 2 to 7 sheets of paper. These membrane functions are an absolute electrolyte, allows the solution to conduct the electricity. So in between that, you can see that we are using certain kind of cell over there. So in between the cell, basically you are using that particular membrane. In this particular case, you see, this is the membrane. So hydrogen, you are having one side hydrogen, you are having the hydrogen ions. So as I told already, it will allow the hydrogen ions to move from one side to another side, and it will not allow the electron very quickly. So in that case, what will happen? When the hydrogen ion and the oxygen, the negative ion will come, they will form the water over there. So by this way, the electricity will store or maybe the form inside that particular systems. So concept: PM fuel cells works with the in the form of a thin permeable sheets and allow hydrogen protons to pass through, but prohibited the passage of electrons and heavier gases, which I was talking about. Now we have what we have done. We have used the graphene oxide nano ribbons assisted proton exchange membrane. So basically, what is happening? So in this particular case, we have taken the PEEK, polyether ketones polymers, and used the titanium dioxides, and we have used the RGONR at the rate titanium dioxide. So basically, we have used the reduced graphene oxide nano ribbons that is modified by the titanium dioxides. So where we can see that it is easily allow the hydrogen ions to go from one side to another side by the hopping mechanism, basically. So by this, or maybe sometimes we are calling it as a Grotius mechanisms also. So by Grotius mechanisms, so basically it is allowing the systems. And earlier days people are using the Naphthalene, probably you have heard it, but Naphthalene is having some drawbacks. So it can go around 80 degrees centigrade because water generation is there. So undoped graphene oxides, boron doped graphene oxides, and the lithium doped graphene oxides. We got very good properties for the lithium doped graphene oxides. So basically, the percentage linearity is 92%, percentage hysteresis is 0.83%, response time is 4 seconds, and the recovery time is 25 seconds. That means how fast the sensor responds to the system, means how fast it is giving that particular, or maybe it is reaching to that particular positions and showing the exact results. And recovery time means after reaching that sensing the 95%, how fast it is coming to its original point. So that is basically known as a recovery time. So this is the examples where we have used this for that humidity sensor. We have worked on the gas sensors also. So two of my students, they have worked. So one, the last student, she has worked on the gas sensors with some magazine materials as well as some PMDs. We have worked on WS2, we have worked on the MOS2, and these papers we have already published in ACS, Applied Materials Interfaces, and Nanotechnologies, Advanced Materials, Advanced Composites, all these journals. So basically, we have worked on the chemi-resistive sensor, so measurement of changes in resistance after the gas absorbed on the surface itself. So basically, there are so many gas sensing techniques, but our sensor works on the chemi-resistive type. So basically, the chemi-resistive means when you are putting that sensors and you are injecting certain kind of gas, or maybe the gases are present into the environment, so automatically the gas will allow change, because it totally depends upon the absorption technology. So measurement of changes in resistance. So resistance change will occur because initially we are going to put a particular voltage over there, and then we are putting a current. So automatically the resistance we are going to measure. So we have seen that when it is into the vacuum, its resistance is something different. When we are exposing into some gases, so resistance is changing. So by changing, by measuring the difference in between the resistance, we can calculate that what is the gas, or maybe the what type of gases, or maybe how it behaves. So basically, this is the fundamentals of chemi-resistive gas sensor. So why graphene is used in sensor applications? So graphene is a unique and attractive sensing materials for gas sensors due to large theoretical surface, specific surface area, that is 2630 meter square per gram. So now you can understand that each and every material at the initial stage, if you remember that I told that there are n number of materials are present, but why we are choosing a particular materials? Because that material should have that capability that it solve my purpose. So I cannot take any kind of random materials over there. So whatever first going to see, or maybe going to check for a particular applications, you have to identify that what is my input parameters, and whether this nanomaterials is able to give the input parameters. Yes, if it is up to that level, maybe yes, then directly go for that nanomaterial. If no, then try to modify that nanomaterial, either maybe the doping, coating, or maybe any other means. Then interaction between graphene sheets and absorbates could vary from weak van der Waals interactions to strong covalent bonding. High carrier mobility at room temperature, that is 2 lakhs per centimeter square per volt per second, with a carrier density of 10 to the power 12 centimeter square, corresponding to a resistivity of 10 to the power minus 6 ohm. So low electrical noise due to its high quality crystal lattice along with its two-dimensional structure. Chemically converted graphene, that is CCG, that is known as reduced graphene oxide for RGO, can be synthesized at relatively low cost in large scale. So graphene-based material used in gas sensor like pristine graphene, people have used graphene oxides, reduced graphene oxides, graphene quantum dots. Now, the chemi-resistive sensor, the fabrications and gas sensing methods. So chemi-resistor is the most widely used configuration of gas sensors. In this case, a gaseous analytes is detected by measuring the resistance change of sensing. Already I have explained to you, introduced by absorbing the gas molecules onto the sensor surface. So how we are making the thin films onto the materials, or maybe onto the IDE basically. So IDE is nothing but the interdigited electrodes. So this is an example, or maybe the image of the IDE. So it is like a comb-like structure. So basically, film deposition methods are either by drop casting, or maybe the spin coating, or maybe the spray coating, or maybe the deep coating. You are putting your materials. Now the thing is that when you are putting some current and voltage over there, constant voltage with varying currents, so basically what is happening, this structure is not connecting each other, so current will not flow. So you are not going to get any kind of resistance or very less resistance based on these particular materials. Now when you are putting certain kind of nanomaterials over there, so nanomaterial is going to create certain channels or maybe certain parts. Here you can see the metal nanoparticles or maybe the graphene is creating certain kind of paths in between that. The current will flow, so automatically the resistance is going to change. So you have to measure that particular resistance, and that is resistance is also very, very negligible. Okay, so advantage, simple fabrications, direct measurements, low cost. So this is basically the gas sensing setups. You are having the dry air, which is nothing but known as the carrier gas. You are purging the basically the hydrogen gas. You are having the MFC, that is the flow capacitor basically. So basically what is happening, it is measuring or maybe it is controlling the flow inside the systems. You are having the digital pressure gauge. You are having some air vent, because when at the vacuum just you are measuring its particular resistance over there. Either you are having the Kitley unit, you are having LCR meter, you are having the thermocouples. You can raise the temperature up to certain, so with temperature also you can measure. And then you are having that iron chamber, chemical sensor, and the hot plate heater below of that particular things to heat up to certain temperature. Now we are having the computer control, so direct the data will come to the computer control, and you can see that how your resistance is changing with the temperature, with the time, or maybe at vacuum, with different flowability of the hydrogen gases, or maybe the different quantity of the hydrogen gases. So we have done certain work on the carbon derivatives in sulfonated polyethylamide, that is a PES basically, PEI. We have done the work on PES also, polyether sulfone. So liquid crystal polymer composites for methanol vapor sensing. So we have used the methanol vapor sensor prepared. We have prepared the methanol. So the substrate we are using the sulfonated polyethylamide with the carbon derivatives. So here you have used the reduced graphene oxides with the polyether sulfonated, and we have measured. So as I told already, this is the sensor mechanisms and the sensing response towards it. So basically the methanol concentrations, how it is increasing and how the sensing response or maybe the percentage response is increasing over there. So we have given certain kind of schematic sensing mechanisms also. We have published these papers into the nanotechnology. So you can get all the details in detail over there. So now what is happening, we have seen certain kind of dynamic sensing response in these particular cases too. Now gas sensor applications, so basically in the process control industries or maybe the chemical industries, you can easily use it. Environmental monitoring, boiler control, fire detections, alcohol breath test, detection of harmful gases in mines, and the grading of the agro products like coffee and spices, where people are using the gas sensor applications. Next, graphene in the biomedical applications. So as I told already, so for some kind of tissue engineering, so artificial tissue, basically you are going to utilize the nanomaterials over there. You are using certain kind of medicines over there. So basically there are various types of biomaterials like metals, ceramics, polymers, and the glass. So polymers, you are making certain kind of stents over there. You are making certain kind of organs made by the polymers. So common use of biomedical polymers, basically electronic devices, drug delivery systems, tissue engineering. So chemicals people are cleaning that Coca-Cola bottle, because sometimes if you open certain kind of old bottle, you can find certain kind of rusting has been taken place at the cap point. So that thus gives us that thing. So thus we have started certain work with the barrier and packaging for the medical applications. So basically we have used certain kind of polylactic acids and the CNC, that is the crystal cellulose nanocrystals combinations with some RGO, and we have made certain kind of thin films which can wrap the which can sustain the food products up to certain time, and after that plastics is basically the biodegradable one. So basically it will not harm to the environment, so it will not hamper, it will keep that particular food for a certain time, say suppose 5 days, 7 days, like that, and it is little bit porous type kind of structure. So when you wrap that food, so oxygen should go inside it, otherwise it will degrade or maybe it will waste it. So that's why we have made certain kind of films which is having certain pores also, by which the oxygen can come into the contact with that particular food and it can keep fresh for a longer time. So this is the motivations of this particular work, and we have published so many good number of journal papers in some reputed journals for this particular topic using the PLA, CNC and the RGO. So basically the CNC we have synthesized from the microcrystalline cellulose, and PLA is the good biodegradable polymer, that is the polylactic acid, and we have used certain kind of RGO which can be used for the tissue engineering also and the packaging and the barrier layer applications. So same thing, we have used some polyethylene glycol grafted TOC-NC, so we have modified the CNC also, so and we have used it for this particular purpose. So we have used some modified cellulose crystals with RGO into the PLA matrix for the biomedical applications. Now this is the targeted drug delivery basically. So the fluorescence assisted, why I am using that particular carbon nano dots or maybe the nano carbon quantum dots or maybe the graphene quantum dots or maybe the nano dots. So fluorescence assisted bioimaging for diagnostic purpose is a highly sensitive, non-invasive and safe detection method. We have developed a novel approach for bioimaging using graphene quantum dots. GQD incorporated the polymeric microspheres. Basically, this project has been funded maybe 5 years back by the Royal Society of Chemistry. So GQD incorporated polymeric microspheres found to be less toxic than other labeling agents like semiconductor quantum dots, organic dyes, fluorescence. I'll show you that how it is giving the image. So when loaded with suitable drug, these microspheres can be used for drug delivery for various medical applications like cancer therapy, gene therapy. So basically, this is the PLA polylactic acids. This is the drug. We are making its cross-linked microsphere small. Then we are coated with some polymers, or maybe sometimes we are using the GQD, and top of the GQD basically we are putting the drugs, oral administrations. So nanoparticles, the drug targeting molecules I am attaching with that. So directly it is going and it is just making the contacts with your affected cells, tumors, because every tumors is having certain receptors. So if unless and until the receptor will not match, that particular medicine will not go and sit over there. So that is the beauty of this particular work. So you can see that 10 micrographs of the GQD, that is the we have formed, we have taken the image in 200 nanometers. This is the photoluminescence spectra of the graphene quantum dots at 461 nanometers. What are the advantages? Selective targeting, toxicity is reduced, less dose is required, reduced side effects, reduced frequency of doses. Of course, there are certain applications like cancer treatment, gene therapy, molecular imaging, biomarker imaging, detection and diagnosis. So this is the image that of the particular our graphene quantum dots, basically GQD. And here you can see that when you put into the cells and then optical microscopy, how it looks like. So you can see, or maybe you can easily label, or maybe you can easily find that how it is moving inside the cells itself. Then we have done certain work on the control shapes and size of the polylactic acid microspheres based on surfactant and polymer concentrations. So still we are working on it, and we have published so many good papers, and also we are trying to work on the your bone cancer too. So here you can find that we have used the Graphene loaded. So this is the very good medicines, cancer medicines for the lung cancer basically. So here also the paid GQD embedded microspheres we have used. So this is the Graphene loaded PEG GQD, how it looks like. So you can easily see that how the layer formations has been taken place, how the coating has been done. So inside we are having the medicines when we are injecting in the body, so it is directly going to the affected sites over there. Then this actually the release. So when it is going inside the body, how the burst release is taking place, how the polymer is dissolving outer side, and slowly the medicine will come out and the whole thing will dissolve inside your body. So this is the actually the degradation process of sample at time intervals of 0, 2, 5, 10, 12, 15, and 20 days basically. So the medicines can sustain for a longer time basically inside the body. We have done certain work on the silver doped TiO2 nanoparticles for the soil techniques for the antibacterial applications. As everybody knows that TiO2 is having very good antibacterial properties. So if you are having some antifungal or maybe the antibacterial problems on your skin, so simple, whatever the cream or lotions you are using, if you check the ingredients, you can find that people are using the TiO2 over there. So the same thing we have applied over here. We have done certain kind of testing over there, and we have taken the silver also with it with varying percentage basically, and then we have done certain kind of testing, and we have done certain kind of advanced synthesis of graphene and composites for the other applications. So I'll very quickly go through. So these all we are having the papers. If you see our website, you can find all the papers details. So this is the convenient method by which we have made the graphene oxides from the rice husk. It is very, very environmental friendly. It is very, very low cost and cheap techniques. So simple rice husk, which is nothing but the wastage. So simply we can make the graphene from it. Then we have made certain kind of graphene oxides onto the growth of carbon nanotubes onto the graphene oxides. So you can find a very good paper by one of the professor from Rice University. He has given the name of it's called the Raman graphene. The concept is same, but we have published it more earlier than him. So basically, in this particular case, the carbon nanotubes vertically extended over the graphene, reduced graphene oxides. So we have done certain kind of titanium dioxide nano flower also. So we have given certain names, that is the nano petals basically. It looks like a kadam flower basically. So this is the very good image we have found for the titanium dioxide nano flower for applications, and it has been done with the RGO. So it is having very good structural and magnetic properties of reduced graphene oxide TiO2 nano flower composites. Then we have done certain kind of nanoclay variations for the graphene oxide nylon 66. One of the MTech students he has done. This is for the basically for the car bumper applications. So for the automobile applications, basically we have done certain work. We have done certain kind of graphene oxides on the thermal and mechanical properties of the amorphous polymers basically. So we have used it for the graphene reinforced aluminum composites. So basically we are working on the aerospace composites also. So we have worked on the aluminum 6061 and 7075 with the silicon carbide and alumina, but here we have used the FSP process, that is nothing but the friction stir processing process basically. So we have introduced, we have reduced the coefficient of friction, we have reduced the wear volume, we have increased the hardness of that particular materials. So basically after and before and after with the FSP process. But one interesting things we have done first time this one, and we have published it already, that is we have done the wrapping of the graphene oxides onto the silicon carbide, and then that wrapped silicon carbide we have incorporated into the aluminum metal matrix composites, and then we have done the whole things are applied for the aerospace applications. So these all are the applications of the graphene-based composites in the aerospace. So there are n number of places where you can use that aluminum metal matrix composites, but nowadays the 60 to 70% has been converted into the polymer people are using for the Kevlar fiber. So Kevlar polymer people are using. It is more lighter and it is having a very good properties than the aluminum composites. This is some future scope. So graphene-based surface heater for de-icing applications. So people are trying to do some work, or maybe some research is going on. So you can think of it. So then people are using graphene-based head tennis rackets. So it will be more lighter weight. It will be more flexible. It is having. It should have the more strength. Then people are working on some graphene-based scaffolds for the bone tissue engineering, some bone regeneration. That is also another important things. People are trying to work on it. They have already started. So basically, they are trying to regenerate the bone. So if it will be possible, and if it will be the tissue engineering scaffold can be possible, then in future that total replacing bone may not be required. So maybe some cases we can regenerate the bone also. So it has been already started very slowly, but so this is my all lab members. So those who are together, we are working together, and we have done this all kind of work. And now thank you very much for your kind patience and listening to me. Thank you.
Thank you, sir. Sir, shall we go with the question and answer session, sir?
Yeah, please. Very quick.
Yes, thank you. Thank you, sir. Thank you. Very few questions we will address, sir. I request participants please type your question in the chat box, or please unmute yourself. You can ask directly to our professor.
Sir, good evening, sir.
Yes, sir. Please, sir. Please.
Sir, can we use the graphene as the heat transfer? Hello, sir.
Please.
Can we use the graphene as the heat transfer application in the heat exchanger, sir?
Yes, people are using nowadays. So many nanofluids has come. Okay, so
Sir,
people are using the graphene nanoparticles over there. But the thing is that it totally depends upon which shape and size you are going to use. Because when you are talking about the heat exchanger, means you have to take the maximum heat, right? So heat
Yes,
rate should be higher. So
Yes, sir.
you can utilize, no problem at all.
and one more question, sir. You said under the graphene having the 1D, 2D, 3D, you said, no, sir?
Yes.
Which one is the better one, sir, for the enhancement of the heat transfer rate?
No, it totally depends. You see, say suppose if I'm talking about the structural applications, so I'll go for maybe for the nanotube kind of things. Okay,
Sir.
because
Sir.
if I try to elongate into its longitudinal side, so automatically I'll get the maximum properties. Okay,
Sir.
but if I go for the nanotubes at the transverse, so it will very easy here. So depending upon that, how you are going to utilize your graphene for which applications, you have to choose the 0D, 1D, 2D, 3D. And sometimes it may happen that maybe suppose you are having some hydrophobic materials or maybe the hydrophilic materials. So that time maybe the graphene oxide work, one time maybe the graphene work, one time maybe the reduced graphene oxide work. So it's totally depends upon your applications.
Sir. Oh, okay. Thank you, sir. Thank you, sir.
Thank you, sir. I request all the participants, you can type your questions through mail, and you will get answers from our resource person through mail. Sir, just 2 minutes, sir. I will wind up with a vote of thanks, sir.
Sure.
Thank you, sir. Thank you. Thank you very much for your wonderful presentation, sir. Your presentation added more value for this short-term training program. Really, it is excellent presentation, sir. You have given good knowledge about the usage of graphene material in all the field, particularly biomaterials field, and it will be very much useful for all the participants, and particularly for the research scholars who are currently doing their research. The takeaway from your presentations are very high. You have started with what is nanoscience and nanotechnology, low-dimensional nanomaterials, and introduction of carbon, allotropy of carbon, and methods of graphene synthesis and its derivatives, structural characterization of graphene, role of biomedical field, graphene-based nanocomposite, and polymer electrolyte fuel cell, graphene sensor, finally graphene oxide applications in aerospace. It is really very informative session, sir. Thank you, sir. Thank you very much, sir. Now I request our convener to conclude this session with thanks to our resource person, sir.
Sir, good evening, sir. Professor Kaushik Paul, sir. So, sir, one more question is there, sir.
Sir, Professor Srinivas, sir, you can ask questions through mail, sir. You will get the answer, sir. Please. Sir, convenient, sir, you can proceed, sir.
So, sir, is it possible to give answer for the question, sir? Kaushik, sir?
Yeah. Just
Uh,
Yeah.
Thank you.
Srinivas,
Thank you, sir.
go ahead.
let me ask.
Please, sir. Srinivas Kumar, please.
Okay, sir. Sir, compounds are used in supers and fuels in application graphene and reducing graphene. Sir,
Please repeat it, sir. Please repeat.
I didn't get your questions because voice is cutting actually.
yes, sir. Sir, somebody are used in fuel applications using the graphene oxide, which is the best to either
Still, I am not getting your questions actually. Audio is not clear.
Srinivas, your voice is low. It's not hearing at all. Not hearing.
Sir, if possible, please type your question in the chat box, sir.
Okay, sir.
Srinivas Kumar, are you there?
Sir, are you typing
The
the
computer,
questions?
sir. Just one, two.
Please, sir, please.
Yeah. Two. Sir, connection, sir. I see two.
Most of the people use graphene oxides or reduced graphene oxide for supercapacitor and fuel cell application. Which one is best, GO or RGO? No, it totally depends upon that because say suppose supercapacitor and fuel cells are totally different. Because in some cases, when I'm talking about the fuel cells, so basically it is coming into the contact with the water. So if I will not allow materials, so basically which will be hydrophilic in nature. So that what will happen, my particular layer, maybe the particular polymer composites will take that particular air, water very quickly, so that it will swallow and it will change its shape and size. But rather in terms of supercapacitor also, so supercapacitor, what I need the reduced graphene oxides because why? Because you see GO and RGO, it's totally depends because RGO when I'm going that I am having the more active sites over there. So if I want to do any kind of modifications, of course I'll go for the RGO case because I'll get more free hands so that I can stick, or maybe the adhesions will be good, or maybe the easier to coating, or maybe any kind of dopings over there. So these all are the reasons. So that's why it totally depends upon the applications to applications. And of course, when you are using the GO and RGO, the properties is also drastically changing. So in some cases, you can see that some properties is going to be reduced. In some cases, some properties is going to be increased. So it's totally depends.
Thank you, sir. Dear participants, please type your question to mail and you will get the answer. Sir, convenient, sir, you can proceed, sir. Yes, sir.
Sir, good evening, Professor Kaushik, sir. Sir, myself, Dr. M. Chandrasekhar Reddy, convener of this STTP, on behalf of management, principal, Department of Mechanical Engineering, and participants, thank you very much for accepting our invitation and delivering webinar talk in AICTE-sponsored STTP on nanotechnology and functional materials, organized by SV College of Engineering, in spite of your busy schedule, and enlighten the participants in recent advances in nanomaterials. Thank you, sir. Thank you very much for your accepting our invitation through mail and reacting in advance. And some changes are also held because we have given some time for you, and afterwards we have changed. We have changed due to technical problem. We We have changed the timing also. Thank you very much, sir. Thank you. Thank you, sir.
Thank you. Thank you very much, you all. Thank you. Thanks for the nice help.
Thank you,
and
sir.
Also giving me the opportunity. Thanks. Thanks a lot.
Thank
Good
you.
luck.
Thank you, sir. Thank you.
Thank you, sir. Please, dear participants, please understand the situation. You can type the question through mail. You will get the detailed answers from our resource person. Thank you. Thank you all.
Sir, could you please provide the mail ID, sir, for the speaker?
Yes, sir. Yes, sir. Sir, Rajesh, sir.
Sir.
Just mail ID type it, sir.
Okay, sir. Okay, sir.
Okay, sir.
శ్రీనివాస్ సార్ మ్యూట్ చేసుకోండి సార్ మ్యూట్ చేసుకోండి.
Dear participants, our today's session is over, and tomorrow's session, Professor Dr. Ajay M. From IIT Kharagpur, characterization of surfaces at micro nanoscale, and afternoon session, Professor Dr. J. Ramkumar, IIT Kanpur, laser micro nano polishing. Our tomorrow session starts at 10 a.m. as usual. I request all the participants, please join 9:45 a.m. itself. Thank you for all.